Alright, so today I'm gonna be explaining another important paper with the title Representation Learning for Frequent Subgraph Mining. This ICML paper in 2020. Identifying frequent subgraphs, also called network motifs, is crucial in analyzing and predicting properties of real-world networks. However, finding large, commonly occurring motifs remains a challenging problem, not only due to its NP-hard subroutine of subgraph counting, but also the exponential growth of number of possible subgraph patterns. So we present this SP minor, stands for subgraph pattern miner, a novel neural approach for approximately finding frequent subgraphs in a large target graph. SP minor combines graph neural networks, order embedding space, and an efficient search strategy to identify network subgraph patterns that appear most frequently in the target graph. SP minor first decomposes the target graph into many overlapping subgraphs, and then encodes each subgraph into an order embedding space. SP minor then uses monotonic walk in the order embedding space to identify frequent motifs. So this is the architecture SP minor encoder A, and SP minor motif search procedure in B. The SP minor decomposes a dataset into many node-anchored neighborhoods and map each neighborhood into a point in the embedding space such that order embedding property is preserved. For example, if neighborhood A is a subgraph of neighborhood B, then A is embedded to lower left of B. And here yellow node anchored neighborhood is a subgraph of both blue and red neighborhoods. So it is embedding to the lower left of both of them. So I repeat again. The SP minor decomposes the dataset into many node anchors neighborhoods and maps each neighborhood into a point in the embedding. This is the order embedding space. So maps each of them to neighbor orbit, and then our walk is just in the order embedding space. And this is a distinction between node anchored and graph level subgraph frequency. We consider a hop node with degree 100 on the left, and we aim to determine frequency of the star motif on the right. So we have a target graph, target vertices, target edges, and G is the query motif. Q stands for query motif. The subgraph isomorphism problem is to determine whether an isomorphic copy of the query graph appears as a subgraph of a target graph G sub T. And this definition is important. The frequency of motif G sub Q in the graph dataset relative to anchor node is a number of nodes U for which there exists a subgraph isomorphism. And so the goal of SP minor is that given a target graph, a motif size parameter K and desired number of results, the goal is to identify among all possible graphs on K nodes the R graphs, for example the motif, with highest frequency. SP minor learnable skip layer. You see, initially all skip connections are assigned equal weights, but B, after training the learnable skip GNN, the model learns the best skip connections. The K-hop neighborhood, anchored at node V, contains all nodes that have shortest path lengths at most K to node V. Subgraph frequency definition uses the concept of node-anchored subgraph isomorphs. We use a categorical node feature to represent whether a node is an anchor V of a neighborhood graph embedded by computing node embeddings through a GNN and aggregated into neighborhood embedding by sum pooling. We define a partial order on the set of all graphs. And if graph A is isomorphic to subgraph B, we write this. And we then assume we are given an embedding function that maps graphs to vectors enforcing the order embedding constraint. To train the SP minor GNN, we need to define a loss function and optimize parameters of GNN to minimize the order. The order embedding penalty between two graphs A and B is defined like this, and we call it the penalty. And to force the order embedding constraint when training, we use this penalty using this max margin loss technique. So our motive search procedure is general, and different strategies can be implemented to navigate the space of motives. And they propose a greedy strategy to improve scalability. At every step, SP miner adds a node such that the total penalty is minimized. So let G prime be chosen by adding one adjacent node to G sub I in G sub T. The greedy approximation simplifies into just a stepwise minimization. And now a beam strategy strikes a balance between the greedy and exhaustive strategies. It also naturally lends itself to Monte Carlo search strategies with neural value function. So you see SP miner versus approximate frequent subgraph mining techniques. And the frequent subgraph identified by SP miner closely match the planted motifs.